Hey guys, this video is about frequency and the wave equation. Alright, so let's start with what frequency means. Frequency has a unit of hertz, alright? It's how often an event occurs. I mean, frequency obviously is that. How frequently do I get up in the middle of the night to go to the bathroom? You know, that's how often I do it, you know? That's what frequency means. But hertz has a special meaning. Hertz means how many of these events or occurrences happen in 1 second. All right, so if something happens, 5 times a second, that's 5 hertz. If something happens once every second, that is 1 hertz. The second hand on a clock, for example, ticks once per second, so it has a frequency of 1 hertz. All right. For waves, we talk about frequency in hertz as the amount of waves produced each second. So if 1 wave is made every second, that's 1 hertz. If it's 10 waves made in a second, that's 10 hertz. All right. A good way to think about hertz is by tapping. It kind of sounds silly, but just kind of watch. Here's 1 hertz, and if I could count like 1 1000, 2 1000, 3 1000, 4 1000, 5 1000. That is 1 tap every second. That's 1 hertz. All right. So if I have 1 second, 1 tap, right? And 5 hertz. How many taps would happen in that second? 1 1000. 2 1000. I think that's 4 hertz. 5 is very hard. It's very quick. I think that's 5. 5 taps in a second. Much quicker. 5 taps. Now a good drum roll, I suppose, would be 20 hertz. If you could get 20 drum taps in a second. Alright? So 1 second, if you get 20 taps, that's like a drum roll. That's not even 20 hertz. Maybe that's 15, but I'm not a good drum roller, I can't get 20 hertz. But what about a decimal amount of hertz, like 0.5 hertz? What would that sound like? Well, that means there's less than a tap every second. Well, 0.5 would more mean that there's a tap every other second, because it's a half a hertz, right? So it'd be like 1 1000, 2 1000, 3 1000, 4 1000, 5 1000, 6 1000, 7 1000, 8 1000. It's more like in 2 seconds you get a tap. It means very infrequent, that you're not tapping very often. If I think about a hertz that's really small, something like that would mean man, I hardly tap ever. It's very unfrequent, but the higher the hertz, the more frequent the event occurs. Alright. Another word about hertz, I'll just flip it over. 60 hertz. Most video games run at 60 hertz. So what does that mean? 60 frames per second for you video game geeks out there like me. Alright? But if you like movies, 24 hertz. 24 frames are shown every second. Those are both more than our eye can make out. But for video games, you need more to make it look more fluid. More pictures every second. Okay. Wave equation. That's what we're going to talk about next. So we took that snaky and we waved the snaky, and we're going to kind of talk about that using an equation. The wave equation is V, velocity, measured in meters per second, equals wavelength, measured in meters, and frequency, measured in hertz. Hertz, in fact, is the same thing as 1/seconds, and that's how you get combined wavelength and frequency. You get velocity. If you multiply wavelength and frequency, meters, and 1/seconds, you get meters per second. So that's your wave equation. Alright. Now, what does the wave equation show? We kind of talked about, we did one demo with it already where we saw high frequency and low frequency, and the wave equation kind of explain what waves look like at a high frequency and what they look like at a low frequency. You can look at the picture here at the bottom of high frequency. That's what a high frequency wave looks like. Alright? And we'll talk about how wave equation explains that. And elongated like this, that's how a low frequency wave looks. It looks very stretched out. So the more frequently waves are made, the more they're packed together basically. But the less frequently they're made, the more they're kind of stretched out. And the wave equation shows that because if you make these waves in the same medium, we know that the velocity depends on the medium. So as long as the medium does not change, the wave speed stays the same. Frequency and wavelength need to multiply to make the same wave speed. So here, when you make waves really frequently and they're really packed together, they get a big frequency, but they get a small wavelength. But if you make them less frequently, they get stretched. They get a long wavelength. So no matter what, the frequency and the wavelength need to multiply to make the same speed, as long as you stay in the same medium, which we will be. Alright? So frequency and wavelength are inversely related. And the reason is that they need to always multiply to make wave speed. So if one goes up, the other goes down, and vice versa. Alright? Here's your wave equation example problem. Alright? We're just going to use the wave equation. It's a very simple equation. I'll just give you a little example problem really quick on how to use it. It says the speed of sound is in air. It's 340 meters per second. So I'm going to say V is 340 meters per second. What is the wavelength, question mark, of sound waves produced by a guitar string that's vibrating very frequently, 490 times a second. 490 up and downs a second, very frequent. Alright, so how would we use the wave equation to figure out what the wavelength on that string is? Alright, well, we could say 340 in for V equals the wavelength times 490. Alright, and there. If you divide both sides by 490, it isolates wavelength all by itself. And take out your calculator, do it with me. 340 over 490 gets you at 2 decimal places 0.69 meters. Remember that the wavelength is the length of a crest and a trough right there, right? So that's how long 0.69 meters is right there.